Okay, the first question we're looking at here is exercise 11E, question 6, and specifically part C, but we need to run through parts A and B just because some of that information is needed a little bit later on. So it says a train travels along a straight track passing from point A at time t equals 0 and passing point B to 40 seconds later. Its distance from A at time t seconds is given by s equals 25t minus 0.2t squared between 0 and 40 seconds. Find the distance AB. Well, okay, so if we draw a diagram, we've got A and we've got B, and the distance t equals 0. The train reaches here at t equals 40 seconds. So hopefully in the first part we got t was equal to 40 and we substituted that into s equals 25t minus 0.2t squared, and that would become 25 times 40 minus 0.2 times 40 squared, and getting an answer there of 680 metres. Okay, so that's part A. Part B says show the train travels with constant acceleration. Well, to do that we're going to have to find the expression for acceleration, and s is equal to 25t, the displacement, minus 0.2t squared. The velocity would be the displacement differentiated, which is 25 minus 0.4t, and the acceleration would be the differentiation of the velocity, which is going to be minus 0.4, and because that's a constant value, the acceleration is minus 0.4 meters per second squared. So that's part B. Now part C introduces this bird. Okay, passes point B at time t equals 0. So we've got a little bird here at t equals 0, passes point B with initial velocity of t equals 0, u is equal to 7 meters per second, straight line between point A with a constant acceleration of 0.6 meters per second squared. Okay, so we've got two things going on here, and then it asks us find the distance from A, at which the bird is directly above the train. So let's say the bird's flying this way, the train's coming this way. At some point, and we'll call that distance x because that's what it's after from A. At some point we've got the train here and we'll have the bird directly above it. Okay, so what we need is an expression for displacement for both, and at that point they will both have the same displacement. Now I'm just going to move this up here so we can get on and see this a little bit clearer. Okay, so this is the point we want, this point here. Okay, now at that point, for the train, our displacement we were given is 25t minus 0.2t squared. And for the bird, well, for the bird, we've got s, we can use see that on this because the acceleration is constant. I mean, it is for the train as well, but we're going to stick with this on here. We're given that displacement anyway. T equals 0, right, so u equals 7. Acceleration is 0.6, and this is the tricky bit here. At the point that we're interested in, okay, the bird, the whole distance would be 680. So the bird must be travelling 680, but minus the x the train has already travelled there. So our displacement here can be written as 680 minus x. Okay, and that's probably the hardest part, I think, to understand of that. Okay, so what can we say? Well, we know at the point of intersection, okay, let's call it x. At x, the displacements must be the same. So 25t minus 0.2t squared must be equal to the displacement of the bird. Okay, now the displacement of the bird, in this case, well, we're going to have to use a Suvat equation. I think you can see we've got SU and A. The time will also be the same, so we can use S equals UT, so half AT squared, which in this case becomes 680 minus X equals ut 7t plus a half times, move up the page, times 0.6 t squared. Simplifying that, we get 680 minus x, 7t plus 0.3 t squared. Okay. And I haven't quite finished this one, haven't I? I've put the displacement there, but we know that displacement at x has a displacement of x. So we've got equation 1 and we've got equation 2. So good old-fashioned simultaneous equations there. Is that all on the page? I think that is. Let's have a look. Yep, good. Okay, so I'm going to sub 1 and 2. And that will give me 680 minus x, 25t minus 0.2t squared, and that's equal to 7t plus 0.3t squared. So processing now, 680 minus 25t plus 0.2t squared is equal to 7t plus 0.3t squared. And I want it equal to 0, it's quadratic. I'm going to subtract everything and add everything from this side. So I make this side 0. That gives me 0.3t squared minus 0.2t squared. 7t plus 25t is 32t. And take away the 680. Now, I don't like this 0.12t squared, so I'm going to times that by 10, both sides of the equation by 10, so we get t squared plus 320t minus 6,800. Looks a bit daunting, but actually it's not too bad. Even if you think how to get that, you can do 340 times 20, those numbers are going to get us close to 320. Now, hopefully we're not resorting straight to the calculator for this, and we are trying to factorise here, but we have a positive and a negative. So we're going to end up with t, what have we got, plus 340, t minus 20. Giving us 2 times of t equals minus 340, which doesn't make any sense, because we can't have negative time, and t equals 20, which does make sense. So finally, that's the time at which the bird is above the train. We just have to substitute that back into the displacement for x, or displacement for the bird, displacement for the train or the bird, I should say. And I'm looking at probably the displacement of the train. It looks a little bit easier, Oh, it makes much difference actually. So I'm going to sub into the train displacement, and I get s is equal to S is equal to 25 times 20 minus 0.2 times 20 squared. Okay, so that gives me, what's that, 500 minus 0.2 of 400 plus 80, I think that is. So we get displacement is 420 meters. And that's it.